All right, welcome back to the next video, everybody. Sorry for the late one today. Today, we're going to be looking at the basic properties of Hecke operators. It'll be a quick one today. So first of all, we'll look at their relationship with the diamond operators. The TP, the Hecke operators T sub P that we talked about last video, they actually commute with the diamond operators diamond sub D. Now, we talked about the diamond automorphisms. The diamond operators are also written like diamond of D, where D is in Z mod and Z cross. And they are operators from SKN to SKN, just like the TP are. And the diamond operators are given by F, maps to F bar sub K delta, where delta in gamma sub 0 of n has lower right entry D when reduced mod n. Any matrix delta with that property will do. This map is well defined regardless of which matrix you pick. And so when I say the TP can meet with these, I mean that TPD equals DTP. And I'm writing function composition here, or operator composition multiplicatively. Okay, and you can also check that the subspaces S sub K of n chi for Dirichlet characters mod n chi, those are also stable under TP. So remember, SKN is like a direct sum over chi of these SKN chi's, right? And so everything that's in SKN is in exactly one of these SKN chi's for some Dirichlet character chi mod n. And so TP will actually send SKN chi to itself. That's what I'm saying. Okay, it also turns out that the TP operators commute with each other. So TP, TQ is TQ, TP for all primes P and Q. That's what I'm saying there. Okay, so these operators are very nice. They kind of commute with everything in sight. We will tie the diamond operators, by the way, to the diamond automorphisms later, when we fully tie the Hecke operators to the Hecke correspondences later as well. Okay, how about Fourier coefficients? So, well, we know that the TP are actually operators from SKN to SKN. And so you might ask the question like, okay, take F in some SKN chi, so in the domain SKN, and give it a Fourier expansion. F of Z equals sum n bigger than or equal to 1 A of n q to the n. You might ask, can we actually write down the Fourier coefficients of T sub P of F? And the answer is yes. And here's what you get. You get the sum over n at least 1, A of Pn. So you get the P times nth coefficient in the nth slot times q to the n plus chi of p, p to the k minus 1, k is our weight here, times the sum over n bigger than or equal to 1 a of n q to the pn. So first we scale the index of the coefficient, then we scale the power of q, and we have this chi of p out front, okay, where chi is the character that's associated with f. Okay, now, if P divides n, we should interpret chi of P as 0, in keeping with the usual convention of Dirichlet characters mod n. That's what we do for characters, okay? So if P divides n, this whole thing isn't even here. You just get this kind of modified version of the Fourier expansion of F, where the indices of the Fourier coefficients have been scaled by P in that case. Now, speaking of the case P divides n, when P divides n, because these formulas are different, sometimes people call the Hecke operators, in that case, U sub P instead of T sub P. So that U sub P of F of Z is just the sum over n bigger than or equal to 1 of A of Pn q to the n. So there isn't, in other words, there isn't this extra term, okay? Now, in general, for my notes, I'll probably just use TP in almost every case. I may occasionally use UP, but it'll be more inadvertent than anything. Okay, the other thing we want to do is we want to know, are there like nth Hecke operators? We've defined pth Hecke operators for P of prime. Are there nth Hecke operators? Yes, there are. The correct way of going about it is like this. First, you define P to the nth Hecke operators just recursively. So if P doesn't divide n, you define T sub P to the n plus first power to be T sub P times T sub P to the n minus P to the k minus 1 power times the composition of operators diamond of P, T sub P to the n minus 1. Okay, so now, if P does divide n, it's easier. T sub P to the n is just the nth power of U sub P. So you just do U sub P n times. You compose it with itself n times. So that's when P does divide n, okay? So then how do you define the nth Hecke operator T sub n in general? What you do is you factor n into its prime decomposition using the fundamental theorem of arithmetic, and you just let T sub n be the product over I of the Hecke operators T sub P to the I to the e to the ith power, where n is the product of P sub I to the e to the ith power. So these primes here and these powers describe the decomposition of n into prime powers. Okay, If you're wondering if a lot of the stuff we talked about in the previous video is still true for T sub n, it is. If you take a congruent subgroup gamma between gamma sub 1 of n and gamma sub 0 of n, it's still true that omega sub t to the nf, so the differential associated to the form T sub nf, it's still obtained by summing the pullback of the differential of associated with f, so f of tau d tau, over all maps describing all cyclic n isogenies of gamma structures. So take your generic elliptic curve, look at all image curves under degree n isogenies with cyclic kernels of size n, pull back the differential of omega f under all of those maps, sum them all up, and you get omega sub t sub n of f, just like we did in the prime case. Okay, it's also true that the t sub n commute with each other. So t sub n, t sub n, t sub m is still t sub m, t sub n for all m and n. And you also get that if m and n have GCD1, that t sub mn is t sub m, t sub n. Okay, and you might ask, all right, well, how about this slide up here where we wrote down the Fourier coefficients for t sub p? Can you do the same thing for t sub n? Yes, you can. I'm not going to write it down. It's not that important for us. The formulas are in Diamond and Sherman chapter 5. In fact, for this video and the last couple of videos and the next couple of videos, I do just recommend like 3 or 4 sources. I like Diamond and Sherman chapter 5. I like the Diamond-Taylor notes on Fermat's last theorem, the section on Hecke operators. And I like Cornell, Silverman, Stevens, Fermat's last theorem and modular forms chapter 3. And then, you know, fill in gaps with PDFs you find online and Math Stack Exchange and stuff like that. Okay, so next time we'll talk about Hecke eigenforms. So thanks for watching, and I'll see you then.